So the beginning of Unit 8 will be the study of these things called polar coordinates. Now, what are polar coordinates? The name sounds pretty weird, polar. No, doesn't have to do anything with North Pole, South Pole. And when you look at them, they seem like high-level stuff. But in actuality, it's a pretty simple system. So let's start off by talking about the definition of a polar coordinate, or the idea of polar coordinates. Although you typically see these in the context of, quote, high-level mathematics, the idea itself is pretty simple. This is simply a system to describe location. It is similar to rectangular coordinates. Rectangular coordinates, you also probably know them as Cartesian coordinates. For instance, this right here is your typical Cartesian or coordinate plane. And this location right here, that physical point in space, we would describe this location as 4, 2, right? Now, why would we describe this location as 4, 2? Because, I guess I should get rid of this period, because from an arbitrary starting point, from the origin, we can see that it is 4 units to the right and 2 units up. So the rectangular or Cartesian coordinate system describes location based upon left and right movements and up and down movements from a particular central location. Polar coordinates does the same thing. It describes location, but instead of using left and right or up and down motions, it describes location based upon angle of rotation and linear distance from the starting motion. So let me go ahead and write that in words. Polar coordinates describe location based upon angular rotation and linear distance from a set starting point. So let's go ahead and get through some vocabulary. In the rectangular system, that starting point is called the origin. In a polar system, it is called the origin as well. If you say the origin to a mathematician, to a professor, they'll know what you're talking about. But in the polar system, they typically call it a pole. Right. So in a Cartesian system, you typically draw a plus, a t. In the polar system, you typically draw a point and a ray. So some vocab words here. This is called the pole. You can also call it the origin. I'm not going to be too fussy. A lot of mathematicians do. And this guy right here is called the polar axis. Every measurement starts at the pole and the polar axis. So for example, before we do example, let's talk about the way we write it, the structure. Right. Rectangular coordinates, recall, you write them as 2 numbers separated by a comma, an ordered pair, x, y. This right here is the horizontal movement. The y right there is the vertical movement. Contrast that with polar coordinates. Polar coordinates uses 2 numbers as well, but it uses an r, theta. Now, theta is pretty straightforward. I'll go ahead and start with that. Theta stands for an angle. But specifically always from the polar axis. And now standard convention still applies. If you go counterclockwise, that's positive angle. If you go clockwise, that's a negative angle. The r is the linear distance from the pole or the origin. You can think of it as the radius. Right? The radius, you start at the center and you go straight to the outer edge. You don't do any twists, you don't do any turns, you don't do any bends. It's a straight linear line. Now, although in rectangular coordinates, we can plot points in any direction. For example, let's go back up to this this page here. If I asked you, hey, plot 4, 2, naturally people would go 4 to the right, up 2, or they could have gone up 2 first and over 4. That's why we call it rectangular coordinates, because in either order that you go, you sort of form a rectangle. You can technically do the same thing with polar coordinates, but here's my suggestion to you. This is a tip. It's not a big necessity, but it's something to make things easier. When plotting polar coordinates, mark or move the angle first. For example, if I asked you to plot 1, 3/4. So this says this point is 1 unit away from the origin, rotated at 3/4 radians. I'm actually going to rotate 3/4 first. Now, I'm not going to say break out a protractor. If this was like the SATs or the ACT, something like very, very strict and picky, go ahead and break out a protractor and measure. As long as you're in the right quadrant and it's not too obviously wrong, I'll go ahead and give you full credit. Just label everything. So what would 1, 3/4 means? It means you're first going to go at an angle of 3/4. Well, we should know that's in the second quadrant. And again, I'm just going to eyeball it. It looks like 3/4. As long as you label, I'll accept it. Next, how do I go through 1? Well, what you do is once you make your angle, just draw tick marks to indicate length, and you just go 1 unit. So guess what? That point there is 1, 3/4. Easy peasy. Let's call it point P. That is 1, 3/4. So I hope it's not hard to visualize this new coordinate system. It's the same. It's basically pre-algebra. You are locating points in space. The only difference is instead of going left, right, up, and down, you are rotating and then marching in a straight line. Do note that positivity and negativity still exists in polar coordinates. When you mark your angle, whichever direction the ray is facing, that's considered positive. Then the opposite direction would have to be negative. So for instance, this blue line here, this blue line right here, that is the terminal side to the angle 3/4. Notice how it's pointing in the top left direction. That I would consider as positive r's. So these guys right here are positive r values, which means if you were to go in the exact opposite direction, if you were facing 180 degrees, do an about face, these guys here would be negative r values. So if I asked you guys to graph a negative anything, a negative angle, a negative r, so for example, if I asked you to plot, I don't know, negative 4, pi-4. Again, when you're plotting polar, I like to do it backwards. I like to do the angle first. So the first thing I'm going to do is plot the angle pi-4, which is right here. I didn't break out a protractor, I just eyeballed it, but as long as I label, I'm fine. But since I recognize that my r is negative, I'm not going to go this direction. Oh no. I'm actually going to go in this direction, the exact opposite direction. So this right here, the dotted line, or the dashed line would be the negative r values, and you just need to go 4 spaces. Again, I'm not going to ask you to break out a ruler. Just draw tick marks and then go 4 spaces. As long as you label everything, I'll give you full credit. So that point P is -4 comma pi fourths. So hopefully you guys can see that for one single point, there's actually an infinite amount of ways you can write it. Points or coordinates are not unique in the polar system, and that's something that's very different than the rectangular system. If I go back to the rectangular system, this physical location in the rectangular system only has one representation, 4, 2. There is absolutely no other way you can write that coordinate in the rectangular system. But in the polar system, every single point, because angles are cyclical, because they go in a cycle, you can have an infinite amount of ways you can write this point. So for example, this point P here, we got to this location, this point P, by first going pi fourths radians and then walking backwards. But who's to say that you couldn't, I don't know, go a negative angle, right? So break out my protractor, do some math. This is -3 pi fourths. And by going -3 pi fourths, this direction is now positive, so all you have to do is walk 4 spaces forward. So this point P is the same thing as +4 comma -3 pi fourths. Right? But what if instead I went all the way around here, right? Do a little bit of math, doing your trig knowledge. That's 5 pi fourths. By going 5 pi fourths, I'm now facing in this direction, so that point P is in the +4 direction. This point here is the same thing as going +4 and going +5 pi fourths. And then you can always generate an infinite amount of answers by going positive or negative coterminal angles. I could go, let's see if I have enough colors. What if I did something like all the way around here, right? That's -7 pi fourths. And since I'm -7 pi fourths, this is the 4 directions you would have to walk backwards. So this is the same thing as -4 comma -7 pi fourths. So you can see here how you can actually represent the same location many different ways. It's all about visualizing. That's what polar coordinates are. It's visualizing a location, not based upon left, right, up, down. That's very strict and rigid, but based upon turns, based upon rotation, and walking forwards or backwards. You just have to play with it. Just dive into it, get a feel for it. On the practice, you're going to be asked to plot points, so just visualize the rotations in your mind, and you're going to be asked to come up with alternative representations. So for example, I might give you the point -4 comma pi fourths and ask you to come up with another coordinate that's equivalent. So I'd be expecting you to come up with this coordinate or this coordinate, depending on the instructions. Now, polar coordinates seem like an unnecessary thing. Gee, Mr. Vo, why am I learning a more complicated way of doing something that I've already learned, which is rectangular coordinates? Well, when it comes to plotting points, life, the Earth, the planet Earth, it isn't as easy as going up and down, left and right. Not every single city was designed like, Central Phoenix, where everything's in a grid. Plus, grid movements are highly inefficient, and when you have the ability to go over terrain, like say in a helicopter or an airplane, we like to go straight to our destination. So in terms of basic navigation, polar coordinates are quite necessary. Speaking strictly in terms of mathematics, polar coordinates sometimes make complicated looking equations nice and easy. For example, the equation of a circle, x squared plus y squared equals r squared, is relatively complicated in the rectangular system. But come tomorrow, you'll find out that in the polar system, equations of circles are simple. But today, I just want to do baby steps. Today, I just want to talk about plotting points. We have to crawl before we can walk. And then tomorrow, we'll handle equations. But what is pretty important is to understand the relationship between polar and rectangular coordinates. And to understand this relationship is to draw a picture that we have drawn 1,000 times back in Unit 6, Unit 5, and in Unit 7 when we did trigonometry. So the best way to find or see the relationship between polar and rectangular coordinates is to plot both of them on the same picture. So what is the purpose of these coordinates again? Is to describe location. So I'm going to pick a random location. Now it doesn't matter what quadrant I pick. For the sake of simplicity, let's put it in the first quadrant. So I know that this one single location can be described using rectangular coordinates x, y, but it also can be described using polar coordinates, which we've just learned is some radius rotated at some angle. Well, let's see physically what these labels entails. If I claim that this point here has a location x, y, let me try to color code this, x, y, again, that means from the origin, you go x distance length horizontally and y distance length vertically. Not surprising, it makes a right angle. If I claim that this point has polar coordinates r, theta, that means from the origin, oops, I forgot what color. I think that's the right color. It is now. From the origin, it has a set length r, and from standard position, it has an angle theta. Gee whiz, what did we just do? We created a right triangle, and hopefully you guys know that we have theorems, we have equations and formulas that connect these two pieces of systems. There are formulas that connect the the rectangular x and y with the polar r and theta. And that's what trig is for. That's what SOHCAHTOA is for. So I hope that we can just see that let's do, I don't know, polar to rectangular coordinates, right? We can see that if I were to look at x, right, and look at the polar coordinates, what trig function relates the box items? Well, relative to the angle, we have an adjacent and we have an hypotenuse, adjacent and hypotenuse. That is clearly cosine. So we can just see that x is r cosine theta, and then the y is r sine theta. These aren't anything new. We developed these relationships back in Unit 5, 6, and 7. So these are the relationships that you would use if you want to go from polar to rectangular. If we want to go the other way around, suppose you had the rectangular coordinates x's and y's, and you want to figure out the polar pieces. Well, let's do it one at a time. So suppose you have the rectangular coordinates x and y, and you wanted to figure out r. Well, that's very easy. The highlighted pieces, they're all side lengths of a right triangle. We have Pythagoras' theorem that connects those three pieces of information. So we can just see that r squared is x squared plus y squared. Well, if we have the rectangular coordinates and I wanted to find the angle, well, of the highlighted pieces, we have an angle, we have an adjacent and opposite side. Angle, opposite, adjacent, that is clearly tangent. So the relationship there is tangent of theta is y over x. So these are the sort of like the bridge between rectangular and polar. If you want rectangular, if you want to convert to rectangular to find x's and y's, you'd use those relationships. If you want to find polars, r's and thetas, you'd use these relationships, and then of course solve for r and theta. Again, these formulas aren't anything new. We've developed these equations before back in Unit 5 and 6. We're just applying it to the context of polar and rectangular coordinates. So with this in mind, it should be seemingly effortless to convert points. Right? So if I asked you to convert 4, 2 pi thirds into rectangular coordinates, you should know that this rectangular coordinates simply mean x, y. So this is just a fancy way of saying, hey, I'm going to give you this information, which again you should know is r comma theta. I'm going to give you r comma theta, and I'm going to ask you to solve for x comma y. Well, what's the relationship? Here are the relationships, so you literally just plug and chug. So to answer this question, I know that x is r for cosine theta 2 pi thirds, and I know that y is r for sine theta 2 pi thirds. And then you just do math, right? So these are special angles, so I'm going to expect you to know how to do it exactly. Cosine of 2 pi thirds is negative 1/2, so negative 2. And sine of 2 pi thirds is rad 3 over 2, which is, what, 2 rad 3? So we know that the rectangular coordinates is x, negative 2, comma, y, 2 rad 3. So those are the rectangular coordinates of this guy. And it should make sense. Like, we can sketch it to prove it to ourselves, even though the instruction doesn't ask. I'm going to do it just for extra anyway. What does 4 comma 2 pi thirds look like? Well, 2 pi thirds is somewhere over here, and I'm going positive 4. See how it's in the second quadrant? Is this point in the second quadrant? Yes, it is. So you know that I don't need to check my answer key. Assuming that I trust my trig, I'm fairly confident that this is the right coordinates. And of course, I'm going to expect you to go both ways. If you can go from polar to rectangular, I'm going to expect you to go from rectangular to polar. So I'm going to ask you to convert 2 comma negative 2 into polar coordinates. And again, all you have to do is know the relationship. So from the above, we know that r squared is x squared plus y squared, and the relationship is that if you take the tangent of the angle, it's y over x. So these should give you equations, starting points to solve for r and theta, because that's what they want. If I ask you for polar coordinates, I'm asking for r comma theta. So let's solve for r. R squared is 2 squared plus negative 2 squared. So that's what? 4 is 8. So r is the square root of 8, which reduces to 2 square roots of 2's. What about the theta? So we have tangent of theta equals 2y, negative 2 over 2. So tangent of theta equals negative 1. Now you have to be very careful, because to solve for theta, we'd have to take the inverse tan. Now, we just have to be mindful of what quadrant we're in. So the original point, 2 comma negative 2, is in quadrant 4. We just have to make sure whatever angle we give needs to be in quadrant 4. So I should know that the reference angle, so if you ignore the negative, tangent inverse of 1 is pi fourths. So if I put pi fourths in the fourth quadrant, I need to figure out what that angle is. So you have two choices. You can do the big positive angle, which is, what's that? Is that 7 pi fourths? Or you can choose to do the smaller negative angle. I really do not mind, because again, for polar coordinates, there's an infinite amount of representations. They're all equivalent. So as long as you give me something mathematically equivalent, I'll mark it as correct. But there we have it. We have all of our pieces. We have our r, we have our theta, whichever one you want to use. So 2 comma negative 2 is the same thing as r comma theta. I'll use the negative angle, pi fourths. Easy peasy. We can do the same conversion thing with equations, with graphs, but I'm going to take things slow and steady. 8.1a is all about getting our feet wet with these polar coordinates. For some of us, it's new. I want us to be able to visualize these polar coordinates, these locations in our mind, and I just want to, take baby steps. Can you convert coordinates? Can you convert points today? And then tomorrow we'll take a look at full-blown equations. So that's it. That is 8.1a. Give it a shot, and good luck. Let me know if you have any questions.